Hello. The last thing we talked about was collinearity, right? And we showed an example, but we didn't say anything about how to quantify collinearity. And I want to continue by speaking about the variance inflation factor. Okay. Okay. What is a variance inflation factor? It's a way to quantify multicollinearity. It's a way to quantify how correlated the different predictors are. It's a way to quantify how much information that one predictor is expressing is already expressed by the rest of them. It's a way to quantify yeah, I think this is it. I don't want to go on. Okay, so imagine X is our design matrix. X is our matrix which has n rows, p columns, n observations, p p predictors, and let's call each column phi. Phi 1, phi 2 to phi p. So phi I is the ith column of X. Now the variance inflation factor is defined as 1 divided by 1 minus r square of j line minus j. So j here refers to the jth predictor, and minus j refers to everything but the jth predictor. So essentially we're saying, what is the r square if we were to regress the jth predictor against the rest of the predictors we have? And if the r square is large, that shows that the predictor we are considering, the jth predictor, there is a linear regression model that can capture the variability in the jth predictor based on the rest of them. So that's collinearity. Okay. So if r squared j based on negative j is close to 1, then collinearity is present. Large VIF. Why? Because if this is close to 1, then this will be close to 0, and then we have 1 over 0. Or 1 over a small number, which is a large number. Now, what is large? I read somewhere rule of thumb is 10, but let's just see what this 10 means. If VIF is greater than 10, that means 1 minus r squared is greater than 10. That means that 1 divided by 10 is greater than 1 minus r squared, meaning that r squared is greater than 0.9. So if the r squared of regressing any variable against the rest of them is greater than 0.9, well, that's a good evidence that there's a significant amount of collinearity. In the example in the book that we covered in the previous lecture, remember, rating and limit were highly correlated, whereas age and limit were not. And we were trying to predict credit based on age and limit or rating and limit. But because rating and limit are highly collinear, the contour plot looked like this, leading to a large standard error, as we can see here. Rating, you see, rating and limit. Rating has 0.9, so this is not bad, but the standard error for limit is large. The t statistic is small, so it's not even significant because these two are highly correlated, so one of them is sufficient. Whereas here, where in model 1 when we had age and limit, because these two were very uncorrelated, this coefficient is actually significant. Now, if we wanted to look at the covariance inflation factor, we see that for age it's 1. So age regressed on rating and limit. The variance inflation factor is close to 1, meaning that r squared is close to 0. Whereas rating regressed on age and limit has a 160 variance inflation factor, and limit on age and rating has a 160 variance inflation factor. So both of these are highly collinear. In other words, rating, information that rating presents is summarized in age and limit pretty well. I mean, it's not probably not much in age, but what we care about is to know whether one of the predictors is telling us something that the rest of the predictors are able to express. And we like to identify that. We want to know about that this is happening. So it gives us some insight to maybe drop it or do something about it at the very least. So next week we will go over all these. We will go over leverage, we'll go over outliers, and we will go over the variance inflation factor using a real data R example.